possible that the first time we hear about the concept of harmonic motion, it is in a physics or mathematics class. There is some irony to this, since the word harmonic is related to the word harmony, which has ancient meanings like agreement of sounds and combination of tones pleasing to the ear. So what is harmonic motion, and what does it have to do with sound and music? In this discussion, we will only be working with simple harmonic motion, which arises when an object of mass m is subjected to a force F toward an equilibrium position where the force is proportional to the distance y the object is from equilibrium. You can demonstrate this for yourself with a simple pendulum. Hang an object from a string. When it is resting, that is equilibrium. If you pull the object back and let it go, you have started simple harmonic motion. In theory, if we were able to remove forces due to air resistance and friction, the pendulum would continue to swing back and forth. If you were to model the back and forth motion of the weight on the pendulum and note its position relative to equilibrium at different points in time, you would get what looks like a sine or cosine wave. You can see an idea of that with this animation. But with some ideas from calculus, we can prove that sine and cosine waves are what model simple harmonic motion. In our ideal scenario, the equations related to the terms we mentioned above would be force proportional to distance, capital F equal negative ky, and Newton's second law of motion, capital F equal ma, where k is a constant of proportionality and a is acceleration due to gravity. In calculus, we learned that the acceleration function is the second derivative of the position function. So we can substitute y double prime for a and set the two equations equal to each other. The result is m y double prime equal negative ky, which gives us the second order differential equation, y double prime plus k over my equal to 0. We learned how to solve this in a differential equations class. But if we consider the functions we discuss in a calculus class, we might be able to see the connection of the second derivative of a sine function to itself and unlock the answer. Same thing with the cosine function. In fact, what we get when we solve the differential equation is one function that represents all solutions to the differential equation. Y equal to capital A sine of the square root of k over mt plus b cosine of the square root of k over mt. Furthermore, with a clever use of the sum formula for sine, we can rewrite the previous solution as y equal to capital C sine of the square root of k over mt plus phi, where capital C is equal to the square root of a squared plus b squared, and phi is the tangent inverse of b over a. We could also get a similar result using a cosine function, but the important point that we have reached is that we can model simple harmonic motion with a sine or a cosine wave. And since these waves also model sound, this tells us why the word harmonic has shown up in the first place. Once again, we visualize this solution with our pendulum animation. The value of capital C is just the maximum distance the weight can reach from equilibrium position. In other words, the amplitude. The frequency is 1 over 2 pi times the square root of k over m, and the phase shift is phi. In this simple animation, when the pendulum weight moves to the right, the related dot on the sine wave moves up, and if the pendulum moves to the left, the dot on the sine wave moves down. Also, when the weight makes one complete cycle of movement, one complete cycle of the sine wave is traced. We can also relate examples of simple harmonic motion to motion along a circle, which can also be modeled by a sine wave. When we relate circular motion to the sine wave, we can also see that the angular velocity is what the quantity square root of k over m represents. Since angular velocity is equal to 2 pi times frequency, then we get angular velocity is 2 pi times 1 over 2 pi square root of k over m, which is just equal to square root of k over m. Now that we have an understanding of simple harmonic motion and how it relates to sine waves, let's look at some ideas in the realm of sound and music. First, if you've ever played an instrument like a guitar or a piano, you'll know that the pitch of a note you play is the same no matter if you play quiet or loud. And if you play one note and then the same note again at a later point in time, the pitch is still the same. This can be seen in our sine wave by noticing that the frequency, 1 over 2 pi times the square root of k over m, is independent of the amplitude capital C and the phase shift phi. This becomes quite useful when we use simple harmonic oscillators for clocks. These clocks also have applications in music, in drum machines, and recording software to keep consistent tempos. The variety of music consists of notes played at certain volumes and pitch, using instruments with varying timbre at varying tempos. It's doubtful that anyone listening to music is picturing a sine wave. But maybe those who studied harmonic motion noticed the relation of amplitude and frequency to those musical qualities and chose the word harmonic to honor that relation.